Thank you very much for the invitation to speak to you today, and thank you for coming. It's quite a pleasure to be able to try and present this talk. It's sort of difficult. Is the sound okay, by the way? I was told I have to stay fixed behind the podium, so it feels a bit unnatural to do that, but I'll do my best. Thank you. So I was telling Doug Boyd that it was a bit of a challenge trying to get this talk prepared, because you know, how can you present what's been done for 15 to 20 years inside of 50 minutes? And he said, well, just imagine that you're going to be presenting to an NSERC review committee that's reviewing your proposal for $5 million. So you're the review committee. You can be the judges at the end. So moving on, what I'd like to do is give you a bit of background as to why this research has been carried on for so long. I want to talk a little bit about the partnership, and that really means talking about a few highlights of what we've been working on this project. And then I think this is probably the highlight, if you will, of the talk, is what does it mean? What benefit is there to anybody? If you look at the Canadian manufacturing sector, and you look at the period, say even over the last four to 5 years, and here I picked the top 10 sectors, and each of these colors represent the different years. So this is transportation, food for the various years. The one I'd like you to focus on is petroleum and coal products. Even though it's gone through a major decline in the last few years, it is still our third highest manufacturing sector in Canada. It's really very important, very critical in terms of its contribution to the Canadian economy. If you look at it a little bit further in terms of analyzing it with respect to Canadian resources, here it is, 90 billion is the capital expenditures, major projects planned. You see a fair chunk of it is again focused on energy-related products, and in terms of the resources, it's a major contributor to our gross domestic product. In terms of our standing in Canada, Sam McEwen was just telling us about nickel. This one's out of date now because he was just telling us it's number 4 in Canada. But we often in MetSoc focus on the metals. We don't quite focus on where we sit in terms of energy in Canada. In terms of natural gas, we're 3rd in the world. And in terms of crude oil reserves, we're 6th in the world. So what does MetSoc or what does materials have to do with any of this? Well, if it's in the ground, you have to transport it. And the most efficient and the safest way still today to do the transporting is by pipeline. There's 840,000 kilometers of pipelines in Canada, and this is how they're broken down. Of those pipelines, only 73,000 are regulated. So that's a lot of pipe that's in the ground transporting a lot of material, and we want to do it safely and we want to do it efficiently. That's where we come in. Here is a map that shows you where the resources are for oil and gas, and this kind of shows you a very miniaturized network of the pipeline networks in Canada already existing. And over here you see essentially there's about 8,000 kilometers of pipeline under construction or in planning. So it is an ongoing activity. It's an important activity. It's important to our economy, and we play as materials engineers a very critical role in delivering that. Now, we're not the only group in Canada that's working in this area. There's Doug certainly contributed for many, many years in this area. There's a group at McMaster who works in the transformation of the steel. UBC does as well. And so we probably have the highest concentration of faculty working in there. And that's because of this. Most of the oil and gas is located and is found in Alberta, and most of the companies are there and they want to transport it out of there. So we have a group of faculty who work in this area. So that was about 15, 20 years ago. Evraz basically came to us and said, we'd like to set up a partnership to study pipeline and do pipeline research. You generate the knowledge, we'll watch what you're doing, collaborate with you, we'll take that knowledge and apply it to our steel and our plants. So I won't cover, of course, everything. I'll just pick some of the highlights that we worked on. I think most people here are familiar with microalloyed steels. Essentially, this is where we are on the banana curve, and we are constantly trying to work with these materials and improve them. However, we may be still in the microalloyed domain. Very early on, this is work that was done with my collaborator Jing Li Luo, looking at corrosion of older pipes and comparing them with newer pipe materials. And here is the reduction of area under SCC corrosion condition divided by the reduction of area of this same material in air. And if you're at 1, you're good. If you're below that, you're not good. You'd like to have that ratio to be as close to 1 as possible. But you also want higher strength. And the reason for the higher strength is then you can then work with higher pressure in the pipeline, higher productivity in terms of transportation. And you see, when you relate these curves to the microstructures of the steels, what this did is essentially led to the elimination of perlite from the steel completely, and the replacement of perlite with various additions of things like niobium to form niobium carbide precipitates. And to what degree, though, does the niobium carbide contribute to this trade-off between the two? So to study that, I'll get to that in a moment, but this is sort of the schematic of the portion of the process that we're going to really initially address. This is after casting. The steel goes through preheating. It goes through some rough rolling and finish rolling, forming the pancake austenite, and then finally accelerated cooling. And this is sort of superimposed over a CCT diagram where you try to control this cooling rate to get you into the right regime of the CCT diagram. And I'll say more about this a little bit later in the talk. And then afterwards comes the coiling part, and in this process here during the cooling, and particularly in the coiling stages where the niobium carbide precipitates form. So first thing we wanted to do is on the runout table is determine what is the cooling rate. And we wanted to do this in the plant. So this is a schematic of the cooling table as it used to exist in Evraz. And so we had a infrared camera looking at the strip after it sort of finished with all the steam and the water that's thrown on it. Had an emissivity probe to make sure that we were getting the right emissivity on the surface of the steel, and comparing that with the pyrometer that was used for process control by Evraz. So this is looking down. What you see is the infrared camera. This is the pyrometer, and this is the infrared camera. This is the emissivity probe, and this is their pyrometer. And this is looking down on this surface, and this is an image of the trailing edge of a strip as it's going by. This is the center of the strip, and so you get an image of the whole strip, but also you can focus on any particular region and get the emissivity and the temperature at that particular regime, that particular region. So here is a sample of the temperature. It's normalized for obvious reasons, but this is the fluctuations of the temperature across the surface of the scalp. This is this particular line here, for example, this point being that one here. And if you look at this in more detail, what you see is these fluctuations in temperature as a function of position. So we, to find the right heat transfer coefficient that will match these variations, we modeled the region of the columns of water that were falling onto the strip, and the strip here is coming at you, and so this is the strip width in this direction. So you can take a certain portion of this where you have the water falling down in a column, you have an impact zone, and then you have the rest of the half of the rest of it, which is essentially a film boiling zone. We do a discretization of that regime, and essentially this is well established in the literature. But what is the impact zone heat transfer coefficient? We basically did the experiments to get the temperatures and then varied this impact zone heat flux until we got pretty much very good matching with the measured temperature profiles. And why this is fluctuating like this is because these zones here, when it's low, is where an impact zone column of water is hitting the surface of the scalp. So having this heat flow model, the question becomes, how do you make sure you can turn these banks of water along the runout table on and off? How do you control, and that's how you control the cooling rate. Well, which ones should be turned on and off to be able to control the rate of cooling, not just of the surface, but either at a quarter thickness or at the center line? And so we put together an optimization model that looked at various variables in terms of which node you look at, which configuration of banks you should be looking at, what should you be doing with side sprays, because every time there's a bank of water that comes down before the next bank, they blow air to get rid of any residual water or steam on the surface. So what should that configuration be, and how do you vary the velocity of the strip? The cost function for optimization is essentially the difference between the desired temperature profile that you want to go through in the CCT diagram to one that you actually obtain from the various configurations that you set in the model. I won't go through in too much detail for this, but just in the interest of time, but here are for example, the various banks, 1, 2, 3, 4, 5, 6, and the side banks are 7 to 12. And essentially, for something like this, you can't just use a simplex search. You have to basically discretize these steps. And so when a 1 appears here in the first set of digits, it means that particular bank is on. In the red digits, it means whether the side spray is on or not. And the 101 represents the velocity of the strip, which we kind of use 3 digits to represent that particular velocity. The velocity of the strip ranges from 3 to 5 meters per second in increments of 0.5. So 3.25 essentially are the 3 digits, 13 to 15. So you basically have to run your heat flow model, you get your temperature data, you compare it with the desired values, and then based on the desired values that you get, you see how far you are off. You then decide which of these you're going to turn on and off, and then you recalculate the heat transfer profile through the runout table, and you keep doing that until you reach your objective. The most efficient way to do that, we found, was using a branch and bound technique. So this is the starting point, and with the starting point you might have a bank that may be on or off, and then this one might be involving the side sprays as well. So the side spray is both on and the bank is on. This one has the bank on but the side spray is off, and this is both off, for example. And so you do your calculation at that point and you see how far you are along the path through the CCT diagram. And then once you pick this one as being the one that's closest to where you want to go, you then go to the next bank and you repeat the same process, and you march along until you reach the very end. And by doing that, you can reduce the number of iterations you're doing for calculations quite significantly. So this shows you, for example, the reduction of the number of steps with a branch and bound. I'll just go back 1 minute. So with 7 banks, that would have led you to 729 simulations. If you do them all rigorously, every single one. But if you do the branch and bound technique and just pick the best ones every time you step through, you can reduce that to a much smaller number of 45 simulations. So that's a major improvement in terms of execution time. So by doing that, I'll start with the table at the bottom here. You can see that looking at various velocities, what the configuration is of the banks and of the side sprays, and what the volume percent of the enthalpy that's retained appears to be. In this case, we were maximizing the enthalpy content of the strip. And so this particular run number 2 gave us the best configuration at 3.25 meters per second, with these configurations shown here indicated. And that particular configuration is shown here through a schematic runout curve for node C, which is the one in the center line, node B, which is a quarter of the way in, and node A, which is on the surface. So that kind of gives you an idea what kind of structure you might end up getting if you follow this particular path here. When we did this work was fairly early in the stage where Evraz was not able to change their configurations in their current runout table, but that led them to the current situation where they've been going through a $200 million expansion and improvement in productivity in their mill. And one of the conditions that they've asked for the runout table was to be able to monitor and change different banks at different times as they wish, to be able to achieve certain microstructures in their product. And this work was partly related and partly responsible for that outcome. This is looking at the 3 different techniques that we looked at for the optimization. This is the generic algorithm. This is the population swarming, and this is the branch and bound. And I think for this audience, you can see that the branch and bound is really the most efficient of the 3 for this particular case. Now, turning our attention to the niobium carbide precipitates, this is looking at the various steels that were looked at. Now, it's been known for years that niobium carbide contributes greatly to the yield strength of these steels. They've been characterized in terms of their size, their location, but how much do they actually, when you look at these numbers here, they're very small. How much do they actually contribute to the strength of the steels in a quantitative way? Well, to do that, you've got to be able to collect these particles from a fairly well representative sample of the steel and be able to then characterize them. And so that's what was done here with these various steels indicated here. The one difference here, you see 3 X100s. All of the ones above the X100s were done in the steel mill. The X100s were done at the pilot mill at CanMet. At that time, it was in Ottawa. So there's a marked difference between the 2 in terms of the precipitates, as you will see. So these are X80s, comparison of X80s. Then there is an X100 that dramatically has different, somewhat different titanium and moly and particularly vanadium levels. And then the three X100s are shown here. The CT to ICT is the coiling temperature divided by the normalized intercoil interrupted cooling temperature. And this is the cooling rates for these steels shown here. Okay, so what was the method that was used? First thing, if you have a sample of steel, you can put it in the SEM and you can get grain size. And that's a quantitative measure. You can make a thin foil out of it and do a TEM and get a precipitate distribution in the matrix. But that's not really quantitative because you don't know what the size of the sample is, and the sample for TEM is rather small. If you do a carbon replica, again, you can get the size and the morphology and the chemistry, but the sample size is small, and the volume of the precipitates, the volume of the steel from which the precipitates come from, is unknown, really. There's too much error associated with it. So Jin Fang developed this matrix dissolution method where you dissolve the sample in HCl, and then you take the sample after it's been dissolved, and this could be anywhere between 10 and 60 grams of steel. You dissolve it, you then centrifuge, and you decant back and forth until you're left with essentially a solution that you analyze in the ICP. And then you're left with, on the other side, a residue where you can do the mass balance in terms of the original sample. This residue of precipitates you can look at with SEM, TEM, XRD, as well as Rietveld refinement. So then you want to basically, we look at the strengthening model where this is the yield stress, this is grain size strengthening, solute solution strengthening, and this is strengthening from precipitates. And I'll come back and show you this again in a bit. So this is measuring grain size for different representative steels that I showed you in the list before. And here you see the strength as a function of mean linear intercept to the -1/2. They follow the Hall pitch pretty well. Now here is the volume percent of nanoprecipitates. These are the ones that are collected from the matrix dissolution method, and they're very small percentages. And this is as a function of the coiling temperature to the interrupt coiling temperature. And you see that there is a trend here that the higher the volume fraction is related to a process parameter that you manipulate on the end of the runout table. Here's an example from the TEM of different precipitates. These are the nanoprecipitates, and these ones are locked into SiO2 because when these experiments, by the way, this you may not see this, but these markers here, micron markers, are 100 nanometers. So that gives you an idea. These are about 5 nanometers in size, these precipitates. The silica comes from the fact that when she was doing the dissolution, she allowed air into the vessel. When we've done these same experiments recently, we've introduced nitrogen to keep the oxygen away, and we can collect these nanoprecipitates without any silica around. The silica did complicate things a little bit, but when you do the EDAX, you can see that they're mainly made up of niobium and titanium. The copper is the grid. Here, and there's a little bit of moly in there, and the silica and the oxygen are, as I said, the background in here. This is a result of the Rietveld refinement, where you can get the precipitate chemistry through Rietveld refinement, because you take those precipitates that you have, now you can run them through XRD and run the precipitate Rietveld on them, and you can also identify what their size is corresponding to each of these different chemistries. And you can see that the 5 nanometer precipitates, this is where the moly is. This is niobium moly carbides. They're not just pure moly niobium carbides. And she was able to close the mass balance between the precipitates and the ICP of the solution back to the original chemistry of the steel. Interestingly, the grade 100 had a much more complicated carbide chemistry for the 5 nanometer materials. The pilot scale materials didn't have any 5 nanometer precipitates in there, so that was a surprise to us. And so in terms of what their contribution of the precipitates are to the X100, we can't really rely on these results for that particular analysis. But where does the niobium go in these steels? Here's the weight percent of niobium as a function of the different steels that we're looking at. The open portion is the amount of niobium in solid solution, and the closed-in bars is that which is in the precipitates. And you can see largely most of it appears in the precipitates, with a little bit all the way through in solid solution. That's important for the calculation of the contribution to strengthening. So here is the original equation I showed you, and that is basically just a linear summation of the different components. There's been other approaches to calculating the strength, and this one looks at the root mean square of the different components of grain boundary, solid solution, and precipitate. And then this one kind of looks at synergy between grain boundary strengthening and precipitate strengthening, but leaves the solid solution and the sigma I separate. So we looked at all these three approaches to see which one actually works. There were measurements of the steel's yield strengths that were done. So this is the yield strength experimental that is measured, and this is based on the precipitate collected, what appears in solid solution, what appears as precipitates, and what the volume fractions are, which is obtained from the dissolution, matrix dissolution method. Here's these points are just a linear summation. But we found that the combination of the root mean square and the linear summation seemed to fit the experimental. So there is some synergy between the solid solution and the grain boundary and the precipitate strengthening that is taking place in strengthening these materials. This, I think, is when I first saw this, I was surprised. Maybe many of you may not be, I don't know. But this is the individual strengthening contribution. So now we can pull out each of the contributions in that equation and see how they contribute to the full strength of each of those steels. And so here is the grain size strengthening that you see colored. The dislocation strengthening is very small. The precipitation strengthening and the solid solution strengthening are those that involve the niobium, and they are nearly, particularly for these steels, because here we don't have any of the 5 nanometer materials, but here you can see that little bit of niobium is contributing to about 40% to 50% of the yield strength of these steels. So a pinch is really having a huge impact on the properties of these steels. And this is kind of now shown in a quantitative way. This has been proven to be quite invaluable in our continuing work with Evraz as they're upgrading their mill, because now people want to go towards thicker walled pipe. And so while they're manipulating their chemistry and checking what their new process parameters are with the new mills, this approach is quite valuable to them to figure out where their alloying elements go, because that way they can see what the strength is and relative to how much money they're spending on alloying elements. The last example I want to look at, and I hope my time is doing okay, is one of the things you have to do once you made the scalp is weld it into the shape of into the form of a pipe. So typically this is for spiral welding for the large diameter pipes. They're usually done through typical processes through tandem submerged arc welding, where you've got 2 electrodes, you supply voltage and current to 2 of them. They basically you form an arc, and you start to weld the steel under a flux that's covering the whole thing. When you're working with thicker walled material, or when you're working with materials that where you want to weld perhaps a little bit faster, the question was, there's an awful lot of latent heat that results in these pools. So the question came about, well, why don't we try to see if we can suck up some of that heat some interesting way. So the idea was to have a trailing electrode, a third electrode stuck into the weld pool, whereas the third electrode is cold. That means you're not putting in any voltage or any current through it. Its sole function is to melt and use up the latent heat that's available into the pool. And that's an example here of this cold wire during the trials that we did at the Avraz R&D Center. So we went through a bunch of tests to see what are the best conditions for introducing this cold wire, and having a high angle 63 degrees was the best one in this case. So we worked with that. These are some of the conditions of the test. I'm jumping through a lot of the work that Mosen did for this particular study. But essentially we were dealing with roughly around 22 kilojoules per centimeter as being a good heat input. And so we decided, all right, let's work with varying some of these parameters, keep that heat input fairly constant, but let's vary the wire feed conditions to see what effect that productivity has on the weld conditions. And that's what the CW1, CW3 represent, and this one basically represents no cold wire added. So what we've seen is that the weld pool dilution, I show you here three cross sections. This is no cold wire added. This is with a cold wire added at this speed. This is the third case with a faster speed. And what you see here is the deposition rate as a function of cold wire feed with the red points. And on the right here is the area of the coarse grain heat affected zone, which is the most critical area in terms of properties in the material. And so as you are speeding the addition of the cold wire, that region is getting smaller, your productivity is going up, so everything initially looks really good. However, you then go ahead and do your micro hardness and you do your Sharpie tests, and something else appears. And so these are averaged over a whole range of hardness measurements done across the face of the fine grain and the coarse grain, and as well as the weld metal. But what you see is that there is the minimum hardness right around the 25 centimeters per minute. And for the Sharpies, this is where the Sharpie notch was located. You see that that has pretty much the higher toughness, even with different temperatures. So you wonder why that is the case. We went and did prior austenite grain size measurements, and these, the ones here seem to be lower than the ones at without the cold wire, but the higher speed seem to have even smaller prior austenite grain sizes. So that wasn't the reason for it. So then we went and looked at MA constituents. And there you see that there is, this is a more detailed plot of this, that the MA constituents decrease as the feeding increases, the feed rate of the cold wire increases. So that isn't entirely the full reason for why we see that difference. Until you look at the morphology of these MAs, and what you see here is that there is a lot more MA, but it's more, how would you say it? It's not as elongated as it is, for example, with the higher speed, and as it is with the absence of any cold wire addition. So being able to have these MA phases finely distributed with a reasonably looking morphology contributed to the better toughness as well as having slightly better hardness, not as hard a structure in that material. So we're looking at this condition a lot more for the thicker walled materials in the current project with EVRAS. This kind of shows you the absorbed energy as a function of the size as well as the spacing of these MAs, again showing you that the one with the first 25 centimeters per minute shows basically the best energy absorbed in both cases with respect to size and also with respect to spacing. So these are the results of the summary of what we get with the cold wire addition, and that is ongoing as we look at the thicker walled materials moving forward. So what was the impact of what we've done over the years that we've done this research? For the industry, what it's done is we've generated new knowledge, and they can kind of see what that new knowledge is and apply it as relevant to their application. They were the first producer of X100, even though it's not really being utilized in North America, but they were the first to do it in North America. We had a small contribution to play in that. They were able to qualify their X80 for Arctic regions for the when people were looking at transporting gas from the Arctic down. That project is on hold for now, but they qualified for that particular application. They've improved their well quality while improving production with the, certainly with the cold wire addition is something that we're going to further improve as well. Slab efficiency has improved. So all of these things have benefited, and they're currently, as I said, expanding their mill with a $200 million expansion. This is an interesting point, particularly for employment in Canada. Is we went through a period where a lot of pipe producers in North America were slowing down and reducing their productivity, but EVRAS still stayed quite productive. From the standpoint of the University of Alberta, we became the leading source of highly trained people for this particular industry. A lot of our graduates do stay in Alberta and work in adjoining companies or related companies in the industry. Some go away and go to France and do PhDs. One in particular in the audience. I think we're recognized for through a couple of awards that we've received, international awards for the research that we've been doing, and that's gratifying. One of the things we take great pride in and satisfaction is that we know that a lot of the steels that are made today for pipelines are far more sustainable than used to be made before, and we contributed to that advancement, as well as I'm sure others, and some of them are in the audience. We've advanced the state of knowledge of advanced microalloy steels for transport in Canada, and also what's not on here is given us an opportunity. What hasn't been revealed, you've seen me talk about optimization, heat transfer, a lot of microstructure evaluations, I'm not an expert in all of these areas. I have colleagues who are. And so this has really provided us a really rich atmosphere to collaborate, get people together to collaborate, and each of us learns from each other as we carry out this research and benefit from that relationship that we have with each other. For the students, every student working on any of these projects ends up with probably 2 or more supervisors, and they do survive through it. They end up learning a lot from each of us, and we learn from their final results as well. The students have access to go and do work at the lab in Regina, as well as do plant trials as needed. They always have an industrial staff person that they collaborate with and talk to on their project. And they carry out some fundamental work on their research, but it has commercial and plant trial implications and some benefits to the steel industry. So that balance between doing the applied and the fundamental, as well as being able to publish their research. And they use state-of-the-art tools, and they develop new state-of-the-art tools in their research. So this is a list of people that have been involved, and I've been happy to be associated with and collaborate with for the last 15 to 20 years. And without all their hard work, I wouldn't be able to be standing here and sharing all this with you today. Thank you.
So have I any question? Yeah, you took that first.
Mr. Henein, when you mentioned that the relationship between the different parameters and the grain and the yield stress, the grain size seems to have the largest effect. My question is, like, the grains you are dealing, they're pancake grain or they're recrystallized grain?
They are transformed grains from pancaked austenite.
But is the Niobium solid solution precipitate has any effect?
Yes, it does, of course. Yes. Yeah, it does. So, I mean, that's not, of course, the niobium contributes to the temperature at which recrystallization takes place, and it contributes to the pancaking, but that's not reflected in the model.
Okay. That was.
Yeah. But it does play a role in the grain size, of course. So their role is more than the 40 or 50% if you take those into account.
Yeah. Yeah.
Okay. Thank you very much for your overview of past a number of years. Yeah, there's so many people involved. Very good results from different kinds of steels, including X100, X80, X70, and so on. Just so you showed also, the X80 is qualified for the Arctic region. So how about the X100?
I think what I've been told by the industry is people have been backing away from the X100. I believe because, and Doug, you might correct me if I'm wrong here, there have been difficulties in being able to get good qualified welds in the field in installing it. And so despite all the efforts that have been done, people have backed away from X100. In fact, even now, with the thicker walled materials that they're looking at, they're going back to X70 as the main workhorse. But they're looking at 25 millimeter thick walled pipe. So very thick material, because they want to still operate at the high pressures for throughput and productivity reasons.
Yeah.
I see that several companies are funding the project. I wonder how the intellectual property is managed so everybody can benefit.
Sure. There's one agreement for the project that all parties have to agree to and sign. Not all the parties contribute the same amount. And so there is an understanding and a trust between all the parties that not all information is shared with everybody. So we will sometimes get samples sent to us from one of the partners, and we will work with it. We might compare it with a sample from another partner, and then when we show them the results is steel A and steel B. We know which is steel A, which is steel B, but we don't share that. So these are things that we very carefully manage to be respectful to everybody in the, so as sponsors in the group. And that the bottom line is they're not interested to know what they are. They're really interested to see how they're how different, what is the knowledge that comes out of the work that is done. So which is steel A, which is steel B, is secondary to knowing what is the contribution of a particular alloying element, for example, or a particular weld pattern, or a particular design for a runout table. So, obviously, Alliance, Enbridge, TCPL are pipeline users. They're not pipeline producers. So the runout table work, for example, they knew that was being done for EVRAZ, and EVRAZ is the major contributor to the project. So yes, it gave them a bit of insight into how the steel is made and why it's made that way, and what variations can occur in the process that could affect the property. So that was knowledge about steel making that they gained that they wouldn't have otherwise bothered to find out about.
Yes.
Thanks for really interesting talk, Hani. I'm sure you're very keenly aware that hydrogen improvement is always a big issue within pipelines. So I'm really interested to know if that new welding process that you've been talking about, with the changes in the microstructure and whether or not that's had an impact.
Good question. Early on, when the early work that I showed that showed perlite, we saw an effect of hydrogen on the steels. We haven't done any tests ourselves, but I know EVRAZ has, and they basically kept telling us, stay away from, don't bother doing any hydrogen work on the newer steels. They don't see an effect on hydrogen on those steels. Very few traps, and even the traps they have are circular and spherical, as you see. So apart from the titanium nitride, which is cubic and might be a little bit an attraction there, but they've gotten us to look more at the low alloyed material for downhole applications, the L80 grades, which I have not had time to talk about those, but we've been addressing the hydrogen particularly in those grades.
Thanks.
Okay, we have a last question. Yeah.
One question is about your three or four different X400, which is manufactured in different areas and COM2017.
It was done in a pilot facility at CanMet.
Anyway, so the microstructure is totally different, and also the straining mechanism is also different.
Very different, yes.
Question is whether all of them are qualified for X100.
No, those steels would not be. They're experimental grades. They're experimental tests. They weren't done for qualification. They were done mainly to see what the process parameters might be for rolling and for cooling, to be able to allow EVRAZ to find the window of processing those. And they've done the processing of X100 in the plant, and I think they have about 2 to 5 kilometers laying in around Ottawa as a test line. But those three steels were experimental steels, were not production steels.
The strength-wise is the same.
They seem to be, yeah, they seem to be okay. But they're not, they didn't have any nano precipitates. But the X100s that they did make in the plant did have nano precipitates. So there are differences between the production and the pilot scale. They don't immediately translate.
Okay, so thank you for your great talk.
Thank you.
And also you say.